What lies inside black holes? They say that truth is often stranger than fiction, and nowhere is this more evident than in black holes. Black holes surpass the wildest imaginations of science fiction writers, yet their existence is a proven scientific fact. The first person to discuss black holes was a Cambridge scientist, John Michell, in 1783. His idea was simple but profound. Imagine firing a particle like a cannonball straight up into the sky. Gravity would gradually slow it down until it eventually stopped and fell back to Earth. However, if the initial speed exceeded a certain critical threshold known as the escape velocity, gravity wouldn't be strong enough to pull it back. The particle would continue into space. For Earth, this escape velocity is just over 11 kilometers per second. For the Sunday, it's around 617 kilometers per second. These speeds far exceed those of any cannonball, but they pale in comparison to the speed of light, which races through space at 300,000 kilometers per second. Light easily escapes from Earth and the Sunday, but Michell hypothesized that there could be stars much more massive than the Sunday, where the escape velocity might surpass the speed of light itself. In such cases, even light emitted by these stars would be dragged back by gravity, rendering them invisible to the naked eye. Michael called them dark stars. Today, we know them as black holes. To understand black holes, we need to start with gravity. Gravity is described by Einstein's general theory of relativity, which is not just a theory of gravity, but also a theory of space and time. The behavior of space and time is governed by a set of equations Einstein formulated in 1915. These equations, unsurprisingly, are known as Einstein's field equations. Despite being the weakest of nature's fundamental forces, gravity holds two distinct advantages. First, it acts over vast distances. Earth orbits the Sunday from a staggering 150 million kilometers away. The Sunday, in turn, orbits the center of our galaxy from a distance of approximately 25,000 light-years. Second, gravity is always attractive, unlike electric forces that can be either positive or negative. This means that in sufficiently massive stars, gravitational attraction between particles overwhelms all other forces, leading to gravitational collapse. For a long time, the scientific community resisted the idea that massive stars could collapse under their own gravity. It seemed inconceivable to predict how such objects might behave. In 1939, Albert Einstein himself published a paper written in 1936 arguing that gravity couldn't lead to the collapse of stars because matter couldn't be compressed beyond certain limits. Many scientists agreed with this intuition. One notable exception was the American physicist John Wheeler, often regarded as the key figure in the story of black holes. Throughout the 1950s and 1960s, Wheeler argued that many stars were destined to collapse. He explored the theoretical challenges this posed and predicted numerous properties of the objects that would form after such collapses, what we now call black holes. For the majority of its life spanning billions of years, a typical star resists gravitational collapse through thermal pressure generated by nuclear fusion, where hydrogen fuses into helium. But eventually, the star's nuclear fuel runs out. The star begins to shrink. In some cases, it stabilizes as a white dwarf, a dense remnant of the stellar core. However, in 1930, Subrahmanyan Chandrasekhar proved that the maximum mass of stars in gravity is limited by gravity itself. He stated that the maximum mass of a white dwarf star cannot exceed 1.4 times the mass of the Sunday. A similar mass limit was calculated by Soviet physicist Lev Landau for neutron stars. So, what happens to an infinite number of stars with masses exceeding the limit of a white dwarf or neutron star once their nuclear fuel is depleted? This problem was studied by Robert Oppenheimer, often referred to as the father of the atomic bomb. In a pair of papers published in 1939, co-authored with his students George Volkoff and Hartland Snyder, Oppenheimer demonstrated that such stars cannot maintain the necessary pressure. Without pressure, a homogeneous, spherically symmetric star must collapse to a point of infinite density, a point known as a singularity. All our theories of space rely on the assumption that space-time is smooth and nearly flat. However, at the point of singularity where curvature becomes infinite, space-time breaks down. In other words, the singularity represents the end of space and time. This notion faced strong objections from Einstein. Then World War II intervened. Most scientists, including Robert Oppenheimer, shifted their focus to nuclear physics, and the topic of gravitational collapse was largely abandoned. Interest in the subject resurfaced with the discovery of distant objects called quasars. The first quasar, designated 3C273, was detected in 1963. Soon after, many others were found. These quasars were extremely bright, despite being located at vast distances from Earth. This emission could not be explained by nuclear processes, as only a small fraction of mass is converted into energy in such reactions. The only plausible alternative was gravitational energy, emitted as a result of gravitational collapse. Thus, gravitational collapse was rediscovered. When this occurs, gravity draws in all surrounding matter. It became clear that a uniform spherical star must collapse to a point of infinite density, a singularity. But what if the star is inhomogeneous and non-spherical? Could the uneven distribution of stellar material cause an irregular collapse, thereby preventing a singularity? In a groundbreaking 1965 paper, Roger Penrose demonstrated, relying solely on the fact that gravity is an attractive force, that a singularity would still form even in this case. At the singularity, Einstein's equations cease to apply. This implies that at a point of infinite density, the future cannot be predicted. Thus, something strange must happen during the collapse of a star. However, this unpredictability cannot affect us if the singularity is not exposed, meaning it is shielded from the outside. Penrose proposed the cosmic censorship hypothesis, suggesting that all singularities formed from the collapse of stars or other objects are hidden within black holes. A black hole is a region where gravity is so strong that light cannot escape. The cosmic censorship hypothesis is almost certainly correct, as numerous attempts to disprove it have failed. In 1967, John Wheeler introduced the term black hole to describe these objects, replacing the earlier descriptions. The new term quickly gained popularity. From the outside, it is impossible to discern what happens inside a black hole. Regardless of what falls into it or how it formed, a black hole looks the same. John Wheeler famously summarized this with the phrase, "Black holes have no hair." A black hole has a boundary known as the event horizon. In this region, gravity is strong enough to prevent light from escaping. Since nothing can travel faster than light, everything else is also pulled back and cannot escape. Falling through the event horizon can be likened to canoeing near Niagara Falls. If you are far enough from the edge, you can paddle away if you row fast enough, but near the brink, nothing can help you. The current accelerates, and the canoe is drawn forward more strongly than the stern. The danger is that the canoe will be swept over the edge. The same applies to black holes. If you fall into a black hole feet first, gravity will pull more strongly on your feet than your head because your feet are closer to the black hole. As a result, you will be stretched lengthwise and compressed sideways. If the black hole has a mass several times greater than the Sunday, you will be torn apart and turned into spaghetti before reaching the horizon. But if the black hole has a mass millions of times greater than the Sunday, gravitational forces will act uniformly across your body, allowing you to pass through the horizon unharmed. So, if you ever plan to explore the interior of a black hole, try to choose a larger one. For example, at the center of our galaxy lies a black hole with a mass 4 million times that of the Sunday. As you fall into the black hole, you will notice nothing unusual. An outside observer, however, will never see your body cross the event horizon. The fall appears to slow down. and your body will seem to hover just outside. Only your silhouette will become increasingly faint, gradually turning red until it disappears from view. From the perspective of the external world, you will vanish forever. If general relativity is correct and the energy density of matter is positive, as is usually the case, then the area of the event horizon, or the boundary of a black hole, must necessarily possess a property such that its area must increase when new matter or radiation enters the black hole. Moreover, if two black holes collide and merge into one, the event horizon area of the new black hole must be greater than the sum of the areas of the two original objects. This area theorem could be experimentally verified at the Laser Interferometer Gravitational Wave Observatory, LIGO. On the 14th of September 2015, LIGO detected gravitational waves from the collision and merger of two black holes. By analyzing the shape of the gravitational wave, the mass and angular momentum of the black holes can be calculated, and the no-hair theorem allows the computation of event horizon areas. These characteristics suggest a similarity between the event horizon area of a black hole and one of the terms in traditional thermodynamic classification. The first law of thermodynamics states that a small change in a system's entropy is accompanied by a proportional change in the system's energy, linking the change in the black hole's mass with the change in the event horizon area. Here, the proportionality factor includes a quantity known as surface gravity, a measure of the gravitational field strength at the event horizon. If we assume that the event horizon area is analogous to entropy, then surface gravity corresponds to temperature. This analogy is strengthened by the fact that surface gravity is the same at all points on the event horizon, just as temperature is uniform across all points of a body in thermal equilibrium. However, while the analogy between entropy and the event horizon area is clear, it remains unclear how this area can become the entropy of the black hole itself. In general, what is the entropy of a black hole? A critical hypothesis was proposed in 1972 by Jacob Bekenstein, who was a doctoral student at Princeton University at the time. His idea was as follows. When a black hole forms as a result of gravitational collapse, it quickly transitions to a stationary state defined by three parameters: mass, angular momentum, and electric charge. As a result, the final state of the black hole does not depend on the nature of the matter from which it formed, whether it was matter or antimatter, nor on its previous state. This implies that a black hole can form from the collapse of a cloud composed of an indefinitely large number of particles of infinitesimal mass. But is the number of configurations truly infinite? Quantum mechanics aligns well with the uncertainty principle, which states that the position and velocity of any object cannot be measured simultaneously. If the position is precisely determined, the velocity remains unknown, and vice versa. In practice, this means that nothing can be localized precisely. Suppose you need to determine the size of a moving object. To do this, you must establish the location of its boundaries. However, this cannot be done precisely, as it would require determining both the position and velocity of the object's boundaries simultaneously. Thus, the object's size cannot be measured exactly. The best you can claim is that the uncertainty principle makes it impossible to precisely define the actual size of anything. Interestingly, the uncertainty principle imposes a limit on object sizes. Simple calculations reveal that for a given object mass, there is a minimum size. This minimum size decreases for heavier objects. The lighter the object, the larger its minimum size must be. This minimum size can be considered a consequence of the fact that, in quantum mechanics, objects can be represented as either a wave or a particle. This results in an object having mass, angular momentum, and electric charge, potentially very large but finite. Jacob Bekenstein proposed that, based on this finite number, the entropy of black holes could be explained. If we examine what happens during the collapse process, we find that a black hole with finite entropy may measure the amount of information irretrievably lost during the collapse leading to the formation of the black hole. The fatal flaw in Bekenstein's argument lies in the following. If a black hole possesses finite entropy proportional to the event horizon area, it must have a temperature different from zero, proportional to surface gravity. This implies that a black hole must be in equilibrium with thermal radiation at a non-zero temperature. However, according to classical theory, such equilibrium is impossible, as a black hole absorbs all thermal radiation incident on it, but, by definition, cannot emit anything in return. It neither radiates nor emits heat. This presents a paradox. The nature of black holes, incredibly dense objects formed by stellar collapse, continues to raise fundamental questions. According to one theory, black holes with identical properties can arise from an infinite number of different types of stars. Another theory suggests that the number of possibilities is finite. This is the information problem. It is believed that each particle and force in the universe contains information. Since black holes have no hair, they might be finite. As John Wheeler once said, an outside observer cannot see what happens inside a black hole. Only its mass, charge, and rotation can be determined. This means that a black hole must store vast amounts of information hidden from the outside world. However, there is a limit to the volume of information that can fit within a given region of space. Information requires energy, and energy has mass and duration. Even Einstein acknowledged that there is no information that exists beyond significance. If too much information accumulates in one area of space, it collapses into a black hole, and the size of that black hole reflects the amount of information. It's like piling more and more books into a library. Eventually, the shelves buckle, and the library collapses into a black hole. If the volume of hidden information inside a black hole depends on its size, then the hole's collapse would correspond to the accumulation of this information. Based on general principles, one might assume that black holes have temperature and should glow, much like a piece of heated metal. But this seems impossible. Nothing can escape a black hole, or so everyone thought. This problem remained unsolved until early 1974. At the time, I was studying how matter behaves near black holes according to the laws of quantum mechanics. To my great surprise, I found that a black hole, contrary to all expectations, emits particles with uniform intensity. Like everyone else, I initially believed that a black hole could not emit anything. I spent considerable effort trying to disprove this seemingly absurd idea, but the more I thought about it, the more stubbornly it refused to disappear. Eventually, I had to accept it. What ultimately convinced me that this was a real physical process was the clear thermal spectrum of the emitted particles. My calculations showed that a black hole generates and emits particles and radiation much like an ordinary heated body, with a temperature directly proportional to its surface gravity and inversely proportional to its mass. Thus, the controversial hypothesis by Jacob Bekenstein that black holes possess finite entropy turned out to be quite persuasive, as it implies that a black hole can exist in thermal equilibrium at a non-zero temperature. Since then, mathematical proofs of black hole radiation have been confirmed by many scientists using various scientific approaches. One way to understand this radiation is through quantum mechanics, which suggests that all space, even near a black hole, is filled with virtual particle pairs that continuously form, separate, and then recombine or annihilate each other. These particles are called virtual because, unlike real particles, they cannot be directly observed by particle detectors. What happens if a cosmic traveler falls into a black hole? They're in for serious trouble. If the hole is of stellar mass, they will be stretched into spaghetti before even reaching the event horizon. If the hole is supermassive, they might cross the horizon without much issue, but will ultimately be crushed into non-existence at the singularity. A black hole with the mass of the Sunday would lose particles at such a slow rate that it would be virtually undetectable. However, much smaller, miniature black holes might exist, with masses comparable to a mountain. These could have formed in the very young universe if it was chaotic and asymmetric. A black hole with the mass of a mountain would emit X-rays and gamma rays with an intensity of about 10 million megawatts, enough to power our entire planet. However, harnessing such a miniature black hole wouldn't be easy. It couldn't be placed in a power station because it would pierce the floor and fall to the center of the Earth. If we had such a black hole, we could only use it by placing it in orbit around the Earth. Efforts to find miniature black holes of this mass are ongoing, but have not yet yielded results. Another possibility lies in creating miniature black holes in extra dimensions. Some theories suggest that the universe we inhabit is merely a 4-dimensional surface within a 10 or 11-dimensional space. The 2014 film Interstellar offers some representation of what this might look like. We can't see these extra dimensions because light can't propagate through them. Light is confined to the 4 dimensions of our universe. However, gravity might influence extra dimensions, and its strength could be far greater there than in our universe. As a result, creating a black hole in extra dimensions might be much easier. This phenomenon could be observed at CERN's Large Hadron Collider. The collider is a 27-kilometer-long circular tunnel where 2 streams of particles travel in opposite directions and collide. These collisions might produce miniature black holes, emitting particles with identifiable characteristics. As particles leave the black hole, it loses mass and shrinks, increasing the intensity of the emitted particles. Eventually, the black hole loses all its mass and vanishes. But what happens to all the particles and unlucky astronauts that fell into the black hole? It seems that all information about what entered the black hole, aside from the total mass and spin, is lost forever. If information disappears, this presents a serious problem that challenges the very foundations of our understanding of science. For over 500 years, we have believed in scientific determinism, the idea that the laws of science dictate the evolution of the universe. If information is truly lost in black holes, we won't be able to predict the future, because a black hole could emit any set of particles. It might even emit a functioning television or a leather-bound volume of Shakespeare's works, though the chances of such exotic events are incredibly small. More likely, it would emit thermal radiation, much like the glow of heated metal. At first glance, the inability to predict what a black hole emits may seem unimportant. After all, there are no black holes nearby, but it's a matter of principle. If determinism, the predictability of the universe, breaks down in black holes, it might break down elsewhere too. There could exist black holes that arise from vacuum fluctuations, swallow one set of particles, emit another, and dissolve back into the vacuum. Even worse, if determinism fails, we cannot be sure of our past history. Historical records and our memories might be illusions. The past explains who we are. Without it, we lose our identity. It is crucial to determine whether information truly disappears in black holes or if it can, in principle, be recovered. Many scientists believe that information must not vanish, but for years, no one has proposed a mechanism for how it could be preserved. This apparent loss of information, known as the information paradox, has troubled scientists for the past 40 years and remains one of the central problems in theoretical physics. Recently, interest in the possibility of resolving the information paradox has been reignited by new discoveries in the field of unifying gravity and quantum mechanics. At the heart of this scientific breakthrough lies the understanding of the symmetry of space-time. Let's assume that gravity doesn't exist and that space-time is absolutely flat. This can be compared to a completely lifeless desert. Such a place is considered to have 2 types of symmetry. The first is called translational symmetry. If you move from one point to another in such a desert, you wouldn't notice any changes. The second type is rotational symmetry. If you stand at any point in the desert and begin to rotate, you wouldn't notice any differences in what unfolds before your eyes. These symmetries also appear in flat spacetime that exists in the absence of matter. However, if you place something in this desert, the symmetry will be broken. Let's say a mountain, an oasis, and a few cacti appear. In that case, at different points and in different directions, it will look different. The same applies to spacetime. When objects are placed in spacetime, both translational and rotational symmetries are broken. Introducing objects into spacetime creates gravity. Gravity in spacetime and spacetime within spacetime. A black hole is a region of spacetime with strong gravity. The spacetime inside it is severely distorted, and we expect symmetry to be broken there. However, as we move away from the black hole, the distortion of spacetime becomes weaker. At great distances from a black hole, spacetime appears completely flat. In the distant 1960s, Bondi, Metzner, Vandenberg, and Sachs made an astonishing discovery. Spacetime at a large distance from matter possesses an infinite set of symmetries, which they called supertranslations. Each of these symmetries is associated with conserved quantities known as supertranslation charges. In this case, a conserved quantity is one that remains unchanged during the evolution of the system. This is an extension of more familiar conserved quantities. For example, if spacetime doesn't change over time, then energy is conserved. If spacetime looks the same at different points in space, then momentum is conserved. What's remarkable about the discovery of supertranslations is that at large distances from matter, from a black hole, there exists an infinite number of conserved quantities. These conservation laws provide an unusual and unexpected perspective on processes in gravitational physics. We know that a black hole has three apparent parameters: mass, charge, and rotation. These are classical charges that have been known for a long time. However, a black hole also contains supertranslations. Perhaps black holes are more than we think. In fact, they are not bald and not just with 3 hairs, but possess a vast number of supertranslation hairs. These supertranslation hairs may contain encoded information about what lies inside a black hole. It's likely that supertranslation charges don't hold all the information, but the rest can be obtained through additional conserved quantities, superrotation charges, associated with additional symmetries, superrotations, about which little is known so far. If this is true, and all information about a black hole can be understood through the indicators of its hairs, then perhaps information loss doesn't actually occur. These superrotation charges may account for the entire entropy of any black hole. Quantum mechanics remains intact, and information is stored on the horizon, on the surface of the black hole. The well-known characteristics of a black hole remain its total mass, electric charge, and rotation outside the event horizon. But the event horizon itself contains information that complements these 3 characteristics necessary to understand what fell into the black hole. The process of understanding continues, but the information paradox remains unresolved. "How did it all begin?" Hamlet said. "I could be confined in a nutshell and consider myself the king of infinite space. Is the universe really infinite? Or is it just very large? Does it have a beginning? Will it exist forever or just for a long time? How can our limited minds grasp the boundless universe? Is it too presumptuous to even try? I am sure we can and should try to understand the universe. We've already made impressive progress in understanding the cosmos. We still don't have the full picture, but I hope we won't have to wait much longer. According to the myth of the Boshongo people from Central Africa, at the beginning of the world, there was nothing except darkness, water, and the great god Bumba. One day, Bumba, feeling a terrible pain in his stomach, strained and vomited the sun. The sun evaporated some of the water, and land appeared. Continuing to suffer from pain, Bumba vomited the moon, the stars, and the premium that fell into Jonah's physical system, so it can't exist for long, otherwise progress would have been much greater. For example, according to Bishop Ussher's calculations, the book of Genesis clearly indicates the beginning of time. It happened at 6 p.m. on the 22nd of October, 4004 BC. On the other hand, the physical environment, mountains, rivers, and the like, has changed little over the course of human existence. They can be considered an unchanging background, either having always existed like a lifeless landscape or having been created simultaneously with humanity. However, not everyone was comfortable with the idea that the universe has a beginning. For example, Aristotle, the most famous of Greek philosophers, argued that the universe exists eternally. Something eternal is more perfect than something created. He suggested that progress could be explained by floods or other natural catastrophes, which periodically reset civilization to its origins. The foundation for believing in the eternity of the universe lies in the desire to avoid the idea of divine intervention in its creation and existence. The question of whether the universe has a beginning particularly fascinated the German philosopher Immanuel Kant. He felt there was a logical contradiction that was intended to create and create anew. He believed that this was not just a contradiction or an antinomy. If the universe has a beginning, why did an infinitely indefinite time pass before it began? He called this the thesis. On the other hand, if the universe existed always, why did it take an indefinitely long time to reach its current stage? He called this the antithesis. The thesis and antithesis are based on Kant's assumption, as well as most others, that time is an absolute concept. That is, it flows from an infinite past to an infinite future, regardless of whether any universe exists or not. This view is also characteristic of many modern scientists. However, back in 1915, it was not defined. Einstein's theory unites space and time, but it says little about space itself. It seems obvious that space, for example, extends in all directions. We don't think the universe ends with a brick wall, although there is no logical reason to assume that this is impossible. Modern instruments like the Hubble Space Telescope allow us to peer into the depths of space. We see billions and billions of galaxies in various forms and sizes. There are giant elliptical galaxies, galactic galaxies. There are spiral galaxies, like ours. In each galaxy, there are billions and billions of stars, many of which may have their own planetary systems. Our galaxy obscures our view in certain directions, but if we disregard this factor, we can say that galaxies are distributed approximately evenly in space, with some local concentrations and voids. The density of galaxies decreases at very great distances. But this is merely an illusion, as they are so far away that we cannot distinguish them. The only thing we can say is that the universe occupies all infinite space and is mostly the same, regardless of how far it stretches. However, while the universe appears uniform, it definitely changes over time at any point in space. You didn't realize this until the early 20th century. Until then, it was believed that the universe was fundamentally unchanging over time. It could exist indefinitely. But this leads to absurd conclusions. If stars emit energy indefinitely, they would have heated the universe to their own temperature. Even at night, the entire sky would be as bright as the sun, because every direction would either be blocked by a star or a dust cloud. The dark sky we see at night has significant meaning. This implies that the universe cannot exist forever in the state we observe today. Something must have happened in the past to ignite the stars. In that case, the light from distant stars simply hasn't had enough time to reach us, which explains why the night sky doesn't glow in every direction. But what does it mean if we see only a dark sky? If stars are supposed to stay in place forever, why did they suddenly light up several billion years ago? What kind of clock told them it was time to begin shining? This puzzled philosophers like Immanuel Kant, who believed that the universe was eternal. But most people were comfortable with the idea that the universe, in roughly its current form, was created only a few thousand years ago, as calculated by Bishop Ussher. However, in the 1920s, observations using the Hooker telescope at the Mount Wilson Observatory began to show inconsistencies with this theory. Most notably, Edwin Hubble discovered that many faint light spots known as nebulae were actually other galaxy-huge clusters of stars, similar to our Sun, but located at vast distances from us. For them to appear so small and faint, the distance must be so great that their light took millions, perhaps even billions of years to reach our eyes. This indicates that the universe couldn't have begun just a few thousand years ago. But Hubble also discovered something even more remarkable. By analyzing the light from distant galaxies, Hubble was able to determine whether they were moving toward or away from us. To his astonishment, he found that almost all of them were receding from us. Moreover, the farther away they were, the faster they were moving. In other words, the universe is expanding, galaxies are moving apart. The discovery of the expanding universe became one of the greatest intellectual revolutions of the 20th century. It was a complete surprise, as it radically changed the direction of discussions. While the universe was once thought to be deeper, it was now seen as broader. In the past, galaxies were much closer together. Judging by the current rate of expansion, one can calculate that 10 minus 15 billion years ago, they were very close. It looks as though, at the moment the universe began, everything was concentrated in a single point in space. Many scientists are uncomfortable with the idea that the universe has a beginning, as it implies a violation of the laws of physics. Some prefer to explain this phenomenon with the presence of an external factor, conveniently labeled God. Thus, theories were proposed suggesting that the universe is currently expanding but has no beginning. One of these is the steady-state theory of the universe, put forward by Hermann Bondi, Thomas Gold, and Fred Hoyle. According to this theory, the expansion of galaxies is explained by the constant creation of new galaxies from matter that allegedly forms continuously in space. Thus, the universe exists forever and always appears the same. This theory has the advantage of being a concrete hypothesis that can be tested through galaxy observations. In the early 1960s, a group of radio astronomers from Cambridge, led by Martin Ryle, studied sources of weak radio waves. They discovered that these sources were surprisingly evenly distributed across the sky and lay beyond our galaxy. Weaker sources were located farther away, and vice versa. The steady-state theory suggested a link between the number of sources and their strength. However, observations revealed more weak sources than expected, suggesting that their density in the past was higher. This contradicted the basic premise of the steady-state theory, which claimed that everything remains unchanged over time. For this and several other reasons, the steady-state theory was eventually rejected. Another attempt to avoid the idea of a universe's beginning was the existence of a past compression stage. However, due to rotation and local inhomogeneity of matter, not all of it concentrated in a single point. Some matter missed the mark, and the universe began to expand again, always maintaining a finite density. Two Soviet scientists, Eugene Lifshitz and Isaac Kalatnikov, claimed to have evidence that in the general case, compression without an ideal system or perfect symmetry must always result in a rebound, with the density remaining finite. This argument was very convenient for Marxist-Leninist dialectical materialism, as it allowed scientists to avoid uncomfortable questions about the origins of the universe. This became a symbol of faith for Soviet scientists. We are accustomed to the idea that the cause of events lies in previous events, which, in turn, happen due to even earlier events. This chain of causality stretches backward in time. But let us suppose that the chain has a beginning and initial event. What caused that event? Few scientists are willing to address this question. They either avoid it, as Russian scientists and supporters of the steady-state theory did, by claiming that the universe has no beginning, or insist that the question of the universe's origin has no answer within the realm of science, or even religion. However, in my view, this position is unworthy of a true scientist. If the scientific laws governing the birth of the universe are suspended, could they also be invalid at other times? A law is not a law if it applies only intermittently, but we are certain that we must try to understand the beginning of the universe on a scientific basis. Perhaps, like many other scientists, we should strive to comprehend the universe's origin scientifically. Please let me know your thoughts. It may be an impossible task for us, but it makes sense to at least try. If Einstein's theory of relativity is correct and certain rational conditions are met, the universe must have had a beginning. Arguing against mathematical justification is difficult, which is why Lifshitz and Kalatnikov ultimately agreed that the universe must have a beginning. Although the idea of the universe's origin may not entirely align with communist ideology, ideologies in general never stood in the way of the development of physics as a science. Physics was needed to build the bomb, and it was important for it to work. However, Soviet ideology hindered progress in biology by rejecting genetics as a science. They demonstrated that the universe began with the Big Bang, when everything that the universe consists of was compressed into a single point of infinite density, a space-time singularity. At that moment, Einstein's general theory of relativity ceases to function. Therefore, it is impossible even to hypothesize how the universe began. All that remains is to assert that explanations for the origin of the universe lie beyond the realm of science. The empirical data supporting the idea that the universe had an extremely compact beginning emerged in October 1965 with the discovery of the cosmic microwave background. These microwaves are no different from those emitted by your microwave oven, just much weaker. They can heat a pizza to only -274 degrees Celsius, which is far too cold to defrost, let alone cook. You may have seen these microwaves yourself. Those who remember analog televisions almost certainly encountered them. When tuning into an empty channel, a few percent of the snowflakes visible on the screen were related to this background radiation. The only reasonable explanation for this radiation is that it originates from an earlier, much hotter and denser state. As the universe expanded, this radiation cooled and gradually turned into the weak remnants we observe today. Many, including myself, are not particularly fond of the singularity concept at the beginning of the universe. Einstein's theory of general relativity ceases to function near the Big Bang, which is why it's called a classical theory. It doesn't explicitly suggest what seems obvious from a common sense perspective, that each particle has a well-defined position and velocity. If we know the positions and velocities of all the particles in the universe, that doesn't mean we can predict how the universe will look. If we talk about the state of the universe at any specific moment in time, we can calculate how things could evolve in the future or the past. However, at the beginning of the 20th century, scientists discovered that they couldn't determine what happens at very small scales. It wasn't that they needed better theories. It turned out that T here is a certain level of randomness or chaos in nature that no theory, no matter how good, can eliminate. This is reflected in Heisenberg's uncertainty principle, introduced in 1927. You cannot precisely measure both the position and velocity of a particle. The more accurately you measure one, the less accurately you can know the other, and vice versa. Einstein absolutely disliked the idea that randomness governed the universe. He famously expressed his thoughts with the phrase, "God does not play dice." But everything seems to indicate that God is in fact a very enthusiastic gambler. The universe resembles a giant casino where dice are rolled or roulette wheels spun at every opportunity. With each throw or spin, the casino owners risk losing money. But with many bets, the odds balance out, and the casino owner is confident that they are not playing dice. That's why casino owners are so rich. The only way to win is to place all your money on a few numbers or dice combinations. The same holds true for the universe. When the universe is large, there are many combinations of how the dice might fall, but on average, the outcome can be predicted. However, when the universe is very small, at the beginning of its development, the combinations are few, and in this case, the uncertainty principle plays a significant role. To understand the origin of the universe, we need to combine Heisenberg's uncertainty principle with Einstein's general theory of relativity. This is an incredibly challenging task for theoretical physicists. In the past 30 years, we haven't been able to solve it, but progress is being made. Let's assume we want to predict the future. Since we know the combinations of position and velocity for a particle, we can't exactly predict how its position and velocity will change. We can only determine the probabilities of specific combinations of position and velocity. This establishes a certain probability for the future of the universe. Now, let's try to think about the past in the same way. What was there before the Big Bang? According to the idea of Aini milieu and the boundlessness of the universe, asking about what happened before the Big Bang is as meaningless as asking where South is at the South Pole, because T here is no reference for time. The concept of time only exists within our universe. Given the nature of the observations we are capable of today, we can determine the probability of a particular history of the universe. The universe must have many possible pasts, each with its own probability. T here is a version of the universe's history in which England wins the World Cup again, though the probability of this is low. The thought that the universe might have multiple pasts might seem like science fiction, but it's a scientific fact. And all thanks to Richard Feynman, who worked at the highly respected California Institute of Technology and played bongos at street intersections in his spare time. To understand the nature of things, Feynman proposed assigning a probability degree to each possible history, using this to make predictions. This works quite well for predicting the future. It's reasonable to assume it might also work for reconstructing the past. Scientists are now trying to combine Einstein's general theory of relativity with Feynman's idea that the universe has multiple histories into a unified theory that will describe everything that happens in the universe. The unified theory will enable us to calculate how the universe will evolve. However, the unified theory alone won't explain how the universe began or what its initial state was. Something more is needed. We must understand the so-called boundary conditions, what can explain the events at the edge of the universe, at the boundary of space and time. If the boundary of the universe is a normal point in space and time, we could cross it and declare the territory beyond it as part of the universe. On the other hand, if the boundary of the universe is jagged, where space or time twists and the density becomes infinite, it would be extremely difficult to define interpretable boundary conditions. So, it's unclear what the boundary conditions should be. It seems there are no logical grounds to prefer one set of boundary conditions over another. It's possible that the universe has no boundaries in space or time. At first glance, this seems to contradict geometric theorems, which show that the universe must have a beginning. They suggest that the universe must have a beginning and that there must be a boundary of time. However, scientists who have tried to refine Feynman's methods mathematically have developed a concept known as imaginary time. This has nothing to do with the real time we experience. Imaginary time has no boundaries. It's not concerned with boundary conditions. We call this possibility the no-boundary proposal. If the universe's boundary has no boundaries, then it truly has no boundaries. It's possible that intelligent beings could evolve without galaxies and stars, but this is unlikely. So, the very fact that we exist and that we as intelligent beings can ask why the universe is the way it is constitutes a constraint on the history we live in. It turns out that this is one of the few histories in which galaxies and stars exist. We call this the anthropic principle. It asserts that the universe must be more or less as we see it, because if it were otherwise, there would be no one around to observe it. Many scientists dislike the anthropic principle because it seems unsatisfactory and unremarkable. But if we weren't in this situation, we wouldn't be able to observe it. It lacks sophistication and doesn't have substantial predictive power. However, the anthropic principle can be stated in precise terms, which is highly significant when it comes to the origin of the universe. M theory, our current best candidate for a unified theory of everything, allows for an immense number of possible histories of the universe. However, most of these histories are simply unsuitable for the development of intelligent life. They are either empty, too short, too extreme, warped, or fail for other reasons. Yet, Richard Feynman's idea of multiple pasts allows for a high probability of such uninhabited histories. In reality, it doesn't matter to us how many such histories may exist without intelligent life. We are only concerned with the subset where intelligent life can evolve. This intelligent life does not necessarily have to resemble human life, nor does it have to exist in three-dimensional space. Little green men may exist, and perhaps in forms we can't even imagine. Humanity itself does not exactly boast of particularly rational behavior. To understand the effectiveness of the anthropic principle, let's consider the directionality of the universe. Common sense suggests that we live in three-dimensional space. In other words, we can determine the position of a point in space with three coordinates, for example, latitude, longitude, and altitude. But why is space three-dimensional? Why isn't it 2, 4, or some other number of dimensions, as seen in science fiction? In fact, in M-theory, space has 10 dimensions, and t here is also an additional dimension time. However, 7 out of these 10 dimensions are thought to be tightly curled up and very small, while the remaining 3 are large and almost flat. This resembles the straw of a cocktail. The surface of the straw is two-dimensional, but one dimension is curled into a tiny tube, making the straw appear as a one-dimensional line at a distance. Why do we live in a history where only 2 of the dimensions are flat and noticeable? A two-dimensional creature would have significant trouble digesting food. If its stomach were inside, as ours is, it would divide the creature in 2, causing it to fall apart. 2 flat dimensions are simply insufficient for something as complex as intelligent life. There is something special about three-dimensional space. In three-dimensional space, planets can maintain stable orbits around their stars. This is a consequence of the gravitational law of inverse squares, discovered by Robert Hooke in 1665 and refined by Isaac Newton. It describes the gravitational attraction between 2 bodies at a certain distance. If the distance doubles, the gravitational force decreases by a factor of 4. If the distance triples, the force is divided by 9, and so on. This law ensures the stability of planetary orbits. Now, let's consider 4-dimensional space. In this case, gravitational attraction would work differently. If the distance between 2 bodies doubles, the gravitational force would decrease by a factor of 8, by 27 if it triples, and by 64 if it quadruples. Such a change in the law of gravity would make planetary orbits unstable. They would either fall into their stars or drift off into the cold, dark expanse of space. The cosmic microwave background radiation is a relic of the very young universe, distributed almost uniformly in all directions. The difference is about 1/100,000th of the total. This extremely small variance needs an explanation. The most widely accepted explanation is that, at one point in the universe's history, there was a period of incredibly rapid expansion. This process, known as inflation, was at least 1 trillion times faster than anything we experience today. This inflation is beneficial for the universe, unlike inflation in prices, which often troubles us. If only inflation had occurred in the universe, the microwave radiation would be perfectly uniform in all directions. So, where do these small differences come from? Quantum fluctuations are a result of the uncertainty principle. Moreover, these fluctuations became the seeds from which all the structures in our universe grew: galaxies, stars, and ourselves. The basic idea behind this process is similar to the phenomenon of Hawking radiation from the event horizon of a black hole. This theory was confirmed some years later, after a decade of research. In 1993, the Cosmic Observatory on the Earth's orbit detected fluctuations in the microwave sky ahead of the actual findings. Cosmology became a precise science 10 years later, in 2003, with the first data from the WMAP satellite. It gave us a remarkable image of the temperature of the cosmic microwave sky, a snapshot of the universe in a state far younger than it is today. The visible deviations predicted by inflation indicate that some regions of the universe have slightly higher density than others. Gravitational attraction in these dense regions slows down the expansion, and eventually these areas may collapse, leading to the formation of stars and galaxies. So, keep a close eye on the map of the microwave sky. It's essentially a blueprint of the universe's structure. We are products of quantum fluctuations at the very early stages of the universe's development. Indeed, God plays Dise. Today, the WMAP's role has been taken over by the Planck Space Telescope, which creates even higher resolution maps of the universe. Planck is thoroughly testing our theories and may even detect traces of gravitational waves, which were also predicted by inflation. Such a discovery would provide a celestial signature of quantum gravity. Could other universes exist? M-theory suggests that an immense number of universes may emerge from nothing, each with its own set of potential histories. Every universe has many possible stories and many potential states in both the present and the future. However, most of these states will have nothing in common with the universe we observe. T here is hope that the first confirmations of M-theory will come from the Large Hadron Collider, LHC, in CERN, near Geneva. From the perspective of M-theory, the LHC operates at low energies, but with a bit of luck, we might see the first hints that the theory is close to the truth, such as the discovery of supersymmetry. I believe that the discovery of supersymmetric partners of known particles would radically change our understanding of the universe. In 2012, it was announced that the LHC had discovered a new particle, the Higgs boson. This marked the first discovery of a new elementary particle. In the years to come, we may uncover new particles that could help create a new chapter in our understanding of the universe. While T here is hope that the LHC will also reveal supersymmetry, even if no new elementary particles are found, supersymmetry might still be discovered at next-generation accelerators. The beginning of the universe, at the moment of the Big Bang, serves as a perfect high-energy laboratory for testing M-theory and our ideas about the creation of space-time and matter. Various theories have been constructed based on traces of the universe's origins. Astrophysical research results could give us hints about the unification of all the forces of nature. So, while other universes might exist, it's unfortunate that we may never be able to explore them. We've learned a lot about the origin of our universe, but there are still two big questions left. Will the universe have an end? And is the universe unique? A good example is the life of a young family, which gradually turns into chaos with the arrival of children. Such conditions are unnecessary for living organisms. For beings like you and me, there are typically two key components: a set of instructions that tells the organism how to act and reproduce, and a mechanism that ensures these instructions are carried out. In biology, these two components are called the genome and metabolism. But it's important to emphasize it here is nothing inherently biological about this. Take a computer virus, for example. A program that copies itself in a computer's memory and spreads information to other computers. This fits the definition of a living organism I provided earlier. Like a biological virus, it is a degenerative form because it only contains instructions or genes, but lacks its own metabolism. Instead, it reprograms the metabolism of the host computer or cell. Some people ask whether viruses should be considered a form of life, since they are parasites and therefore depend on other forms of life for survival. But in that case, most life forms, including ourselves, are parasites, as we rely on other life forms for sustenance. I believe computer viruses should be considered a form of life. This could say something about human nature, as the only form of life we've managed to create so far has been exclusively destructive. Let's not even talk about attempts to create life in our own image. But I will return to electronic forms of life later. What we typically understand as life is based on chains of carbon atoms with some other atoms, such as nitrogen or phosphorus, mixed in. One could imagine life based on a different chemical foundation, such as silicon. but carbon seems the most suitable because of its exceptional ability to form various types of chemical bonds. The fact that carbon atoms must be present everywhere, with the properties they have, requires a fine-tuning of several physical constants, such as the quantum chromodynamic scale, electric charge, and even the number of space-time dimensions. If these constants had significantly different values, either the nuclei of carbon atoms would be unstable or the electrons would not work as they do. In general, all these constants we have can only be present with their true values. Therefore, we must be cautious in saying they don't matter. Perhaps this shows that we can't create the entire universe to be just right for the emergence of the human race. But we should be careful with such arguments due to the anthropic principle, which holds that our theoretical understanding of the universe is based on an obvious truth. If the universe weren't conducive to life, we wouldn't be asking why it's so finely tuned. The anthropic principle is often divided into strong and weak versions. The strong anthropic principle suggests that there are many different universes, each with varying values of physical constants. In some of these universes, the values are conducive to the existence of things like carbon atoms, which act as building blocks for living beings. Since we must live in one of these universes, it's not surprising that the physical constants are so finely tuned, otherwise we wouldn't be here. However, the strong anthropic principle doesn't seem very useful, because what practical significance do all the other universes have in this case? And if they are separated from ours, how can they influence our universe? Personally, I prefer the weak anthropic principle. I accept the values of the physical constants as given, but I want to understand what conclusions can be drawn from the fact that life exists on this planet at this stage of the universe's history. 13.8 billion years ago, when the Big Bang occurred and the universe was born, carbon didn't even exist, let alone be known. It was so hot that all matter existed as particles, which we call protons and neutrons. Initially, there were equal amounts of protons and neutrons. However, as the universe expanded, it cooled down. About a minute after the Big Bang, the temperature had dropped to about 1 billion degrees, which is 100 times hotter than the core of the Sunday. At this temperature, neutrons began to decay, creating more protons. If this had continued, all the matter in the universe would eventually have consisted of a simple element hydrogen, whose nucleus contains a single proton. However, some neutrons collided with protons, fused together, and formed another simple element helium, which has a nucleus consisting of 2 protons and 1 neutron. But in the early universe, heavier elements like carbon and oxygen could not form. It's hard to imagine a living structure made solely of hydrogen and helium. In any case, the early universe remained too hot for atoms to form molecules. The universe continued to expand and cool, but in some regions the density was slightly higher than in others. There, gravitational attraction of additional matter slowed down the expansion until it came to a complete halt. The collapse of matter began to lead to the formation of stars and galaxies, starting about 2 billion years after the Big Bang. Some of the first stars must have been more massive than our Sunday. Their temperatures were also higher, which helped transform the initial helium and hydrogen into heavier elements like carbon, oxygen, and iron. This process could have taken several 100 million years. As a result, some stars exploded, becoming supernovae and spreading heavy elements into space, which became the raw material for new generations of stars. Other stars are too far away for us to directly observe whether they have planetary systems. However, there are 2 ways to detect planets around stars. The first is to track the star and observe if the light it emits remains constant. If a planet passes between the star and the observer on Earth, it slightly dims the light from the star. If this happens regularly, it means the planet is orbiting the star. The second method involves precise measurement of the star's position. If a planet orbits the star, it causes a slight wobble in the star's position. If the wobble occurs repeatedly and regularly, it suggests that the star has at least 1 planet. These methods were first applied about 20 years ago. Today, thanks to them, several thousand planets have been discovered orbiting distant stars. So why wouldn't a galaxy be teeming with self-regulating mechanical or biological forms of life? Why isn't Earth colonized or even visited? By the way, I strongly disagree with the idea that UFOs might be carrying extraterrestrial beings. I think any visit from aliens should be more noticeable and, most likely, quite unpleasant. So why aren't we being visited? It's possible that the probability of life spontaneously arising is so incredibly low that Earth is the only planet in the galaxy, even the observable universe, where it has been possible. T here is another possibility. It could be that T here is a real chance for self-replicating systems, like cells, to form, but most of these life forms never evolve to the level of intelligent beings. We tend to think of intelligent life as an inevitable result of evolution, but is that really the case? The anthropic principle reminds us that we must be cautious with such assumptions. Evolution is more likely a chaotic process, and the emergence of intelligence is just one of many possible outcomes. It's not even certain that intelligence is beneficial for long-term survival. Bacteria and other single-celled organisms might persist, even if all other life on Earth is wiped out by human activity. Perhaps intelligence wasn't a promising direction for the formation of life on Earth, given that it took 2.5 billion years to evolve from single cells to multicellular organisms, the necessary precursors for intelligent life. This is quite a long stretch of time before the sun dies, which aligns with the hypothesis that the probability of intelligent life emerging is extremely low. If that's the case, we may find many other forms of life in the galaxy, but it's unlikely we'll encounter intelligent beings. Life may not evolve into intelligent forms for another reason as well. For example, a planet might collide with an asteroid or comet. In 1994, we witnessed the collision of the Shoemaker-Levy comet with Jupiter, which led to several giant fireballs. It's believed that a collision of a relatively smaller body with Earth 66 million years ago caused the extinction of the dinosaurs. A few species of small early mammals survived, but anything as large as a human was almost certainly wiped out. It's difficult to say how often such collisions occur, but it's reasonable to assume that their periodicity is about 20 million years. If that's the case, then intelligent life on Earth only emerged thanks to a lucky accident that nothing similar has happened in the last 66 million years. Other planets in the galaxy where life formed may not have had such a long period of stability without global catastrophes big enough to hinder the evolution of intelligent beings. A third possibility is that life might indeed form and evolve into intelligent beings, but then the system becomes unstable and intelligent life destroys itself. This is a very pessimistic scenario, and I hope it's not true. I prefer the fourth possibility, that there are other forms of intelligent life in the cosmos, but we simply don't notice them. The Breakthrough Listen project is an initiative focused on searching for extraterrestrial intelligence. It involves observing the night sky using 2 radio telescopes with the most advanced equipment available. The project is generously funded and benefits from thousands of telescope hours. Currently, it is the world's largest scientific program dedicated to the search for evidence of extraterrestrial civilizations. T here is also the Breakthrough Message Project, an international competition to create messages that could be understood by advanced civilizations in space. However, since we haven't advanced far enough ourselves, we must approach the possibility of receiving such messages with caution. At our current stage, an encounter with a more advanced civilization might resemble the encounter between Native Americans and Columbus, and I doubt the natives were thrilled with that encounter. Should we explore space? What's the point? How can we justify the enormous efforts and money spent just to bring a few rocks from the moon? Aren't there more important issues on Earth? The obvious answer is right here, around us. Staying on Earth is like sitting on a deserted island after a shipwreck and not trying to escape. We need to explore the solar system to find places that are suitable for human habitation. In a way, this situation is similar to Europe before 1492. Many people probably thought it was crazy to encourage Columbus to throw money away, but the discovery of the New World turned out to be a huge advantage. Perhaps it will have an even greater impact on the Old World. Just imagine living without Big Macs or KFC. Our expansion into space will have an even greater effect. It will completely change the future of humanity and could even determine whether we have a future at all. It won't solve any immediate problems on Earth, but it will give us the opportunity to look at those problems from a different perspective and will make us look more ahead than behind. I hope it will unite humanity. Of course, this is a long-term strategy. When I say long-term, I mean hundreds or even thousands of years. In the next 30 years, we might build a base on the moon. In 50 years, we could reach Mars, and in 200 years, we might explore the moons of other planets. I am talking about manned flights. Rovers are already roaming Mars, and we've landed a probe on Titan, Saturn's moon. But if we want to advance humanity's future, we need to go there ourselves. Space travel isn't cheap, but it will only require a tiny fraction of the world's resources. NASA's budget has remained fairly steady in real terms since the Apollo expeditions, but it's dropped from 0.3% of the US GDP in 1970 to 0.1% in 2017. Even if we increase the international space budget 20-fold, it wouldn't mean we can't do it. To seriously engage in space exploration, it would only represent a small fraction of the global GDP, of course. Some will argue that this money should be better spent on solving earthly problems like climate change or environmental pollution, rather than possibly investing in business ventures. But on the 20th of July, 1969, Neil Armstrong and Buzz Aldrin made the first successful landing on the moon. That changed the future of humanity. The space race sparked a renewed interest in science and accelerated technological progress. Under the influence of the lunar expeditions, many scientists came to science with the goal of learning more about ourselves and our place in the universe. The world gained new perspectives that allowed us to see the planet as a whole. However, since the last lunar expedition, we haven't been able to see the planet from space. Perhaps we never will again. One of the main reasons for this is unpredictability. At a time when there were no plans for manned space flights, public interest in space faded. This coincided with a general disillusionment with science in the West. While it certainly brought much benefit, it didn't solve the pressing social issues that garnered more attention. A new program for manned space missions could play a major role in rekindling public enthusiasm for space and science in general. But that hasn't been the main focus for us. For us, the main focus has been on robot missions, which are much cheaper and may provide more scientific information, but they can't capture public attention in the same way. And they don't take humanity into space, which, I insist, should be our long-term strategy. The plans for establishing a lunar base by 2050 and sending humans to Mars by 2070 could activate the space program, giving it new significance, much like President Kennedy's announcement in the early 1960s. At the end of 2017, Elon Musk revealed SpaceX's goal to build a lunar base and conduct a manned mission to Mars by 2022. Meanwhile, President Trump signed a directive to shift NASA's focus towards space exploration and discovery, making it possible that we might get there even sooner. This renewed interest in space could elevate the reputation of science in the eyes of the general public. The decline in respect for scientific pursuits has serious consequences. We live in a society where science and technology play a crucial role, yet fewer young people are entering these fields. A new, ambitious space program could spark the interest of youth, inspiring them to engage in various areas of science, not just astrophysics and cosmology. But as cosmologists and astronauts, we won't necessarily delve into cosmology. That's a whole different challenge. Can humans survive outside Earth for extended periods? Experiments on the International Space Station, ISS, have shown that humans can live and work for many months away from Earth. However, the microgravity environment in orbit causes several undesirable physiological changes. A planet or moon could also become a source of raw materials essential for sustaining a human community independent of Earth. Where in the solar system could we establish human colonies? The most obvious candidate is the Moon. It's close and relatively easy to reach. We've already walked on it and even drove rovers across its surface. However, the Moon is small and lacks an atmosphere or magnetic field to shield against solar radiation, unlike Earth. Tea here is no liquid water, although ice might be present in the craters near the poles. Lunar colonies could extract oxygen from this ice, using nuclear energy or solar panels. The Moon could serve as a launch pad for further exploration in the solar system. The next obvious target is Mars. It lies 1.5 times farther from the Sunday than Earth, meaning it receives about half the amount of heat. Mars once had a magnetic field, but it disappeared about 4 billion years ago, leaving the planet unprotected from solar radiation. This resulted in the loss of nearly all of Mars's atmosphere, which is now just 1% of Earth's. However, in the past, atmospheric pressure might have been higher, as evidenced by what we believe are dried-up riverbeds and lakes. Currently, liquid water cannot exist on Mars's surface due to the almost complete vacuum. It would evaporate. Yet, there could have been a warm, wet period when life may have arisen either spontaneously or through panspermia, meaning it was brought from elsewhere in the universe. While T here is no evidence of life on Mars now, finding proof that it once existed would suggest that the potential for life on this planet is quite high. Nonetheless, we must proceed cautiously to avoid contaminating Mars with Earth's life forms. This would require precautions to ensure we don't inadvertently introduce Martian life to Earth, as we have no immunity to it, and it could pose a threat to life on our planet. NASA has sent several spacecraft to Mars, starting with Mariner 4 in 1964. Various orbiters have also studied the planet, and the most recent was an interplanetary probe, the Mars Reconnaissance Orbiter. These missions have revealed deep valleys and the tallest mountains in the solar system. NASA also landed several probes on Mars, including 2 rovers, which sent back images from the planet's barren, desert-like landscape. As on the Moon, water and oxygen could be extracted from the polar ice caps on Mars. Mars has experienced volcanic activity, which may have left valuable metals and minerals near its surface sources that would be crucial for future colonists. The Moon and Mars are the most viable locations for human colonies within the solar system. Mercury and Venus are too hot, and Jupiter and Saturn are gas giants without solid surfaces. Mars moons are small and don't offer any advantages over the planet itself. However, some of Jupiter's and Saturn's moons could be promising candidates. But what if we venture beyond the solar system? Observations show that many stars have planetary systems. So far, we can only detect giant planets like Jupiter and Saturn, but T here is reason to believe that smaller, Earth-like planets may be in orbit around these stars. Some of these planets may lie in the habitable zone, the distance from a star where liquid water can exist on the surface. Within 30 light-years of Earth, there are about 1,000 stars. Even if just 1% of them have Earth-like planets in the habitable zone, we could have around 10 candidates for new worlds. One example is Proxima b, an exoplanet located just 4.5 light-years away from Earth. It orbits Proxima Centauri in the Alpha Centauri star system. Recent studies show that it shares many similarities with Earth. Traveling to these potential new worlds is currently impossible with our existing technology. But who's to say we can't imagine interstellar travel far in the future, say, 200 or 500 years from now? Rocket speed is determined by 2 factors: the velocity at which exhaust gases are expelled and the amount of mass the rocket loses during acceleration. The exhaust velocity of chemical rockets, which we currently use, is about 3 kilometers per second. By shedding 30% of its mass, a rocket can achieve a speed of about 0.5 kilometers per second. This speed gradually decreases. According to NASA's calculations, a trip to Mars could take about 260 days, plus or minus 10 days. Some experts, however, suggest it could be done in 130 days. But even at such speeds, a journey to the nearest star system would take around 3 million years. To travel faster, we would need much higher exhaust velocities than those achievable by chemical rockets. A better option could be light itself. A powerful beam of light from the rear of a spacecraft could propel it forward. Nuclear fusion might provide 1% of the spacecraft's mass and energy, enabling it to accelerate to 1/10 the speed of light. To go faster, we would need either matter-antimatter annihilation or some entirely new form of energy. In reality, the distance to Alpha Centauri is vast. To reach it within a single human lifetime, a spacecraft would need to carry fuel equal in mass to that of all the stars in the galaxy. In other words, interstellar travel is currently impractical with our existing technologies. We are undoubtedly entering a new era of space exploration. The first non-governmental astronauts will be pioneers. The initial flights will be incredibly expensive, but I hope that over time, space travel will become accessible to more people on Earth. Sending more and more passengers into space will give new meaning to our existence on Earth and our responsibility as its stewards. This will also benefit the Moon, as it will help us better understand our place and future in space. I hope that space holds the key to humanity's future. Breakthrough Starshot represents a real opportunity for humanity to begin its foray into space with the goal of evaluating and testing the prospects of colonizing it. This mission aims to test and confirm a series of conceptual ideas, including miniaturizing spacecraft, creating light sails, and developing laser propulsion systems. To achieve this, we must improve the results. A Starship, a fully autonomous space probe, just a few centimeters in size, will be attached to a light sail. The sail, made from metamaterials, weighs no more than a few grams. The plan is to launch thousands of these probes into space, each equipped with a light sail. On Earth, a group of lasers, arranged over an area of 1 square kilometer, will focus their laser beams into space. These lasers will not only power the probes but also serve as the backbone of this mission. The laser beam, with a power of tens of gigawatts, will pass through the atmosphere and accelerate the sail. This innovative concept echoes the dream of a 16-year-old Einstein who once imagined flying on a beam of light. The probe will accelerate to just 20% of the speed of light, but that still equates to 160 million kilometers per h-hour. With such a system, it could reach Mars in less than an hour and Pluto in a matter of days. Within a month, the probe would pass by Mars, overtaking Voyager in just a week, and reach Alpha Centauri in 20 years. Once there, the probe could take photos of planets in the system, check for magnetic fields, and look for organic molecules, sending the data back to Earth using the same laser system that launched it. This signal would take approximately 4 years to reach us. It's worth noting that the trajectory of the probes could include a flyby of Proxima b, an Earth-like planet located in the habitable zone of its star, Alpha Centauri. In 2017, the Breakthrough Project partnered with the European Southern Observatory to enhance the search for potentially habitable planets in the Alpha Centauri system. The Breakthrough Starshot project has other secondary goals, such as exploring the solar system and detecting asteroids that cross Earth's orbit. German physicist Claudius Gross suggested using these technologies to create a biosphere of single-celled microbes on temporarily habitable exoplanets. In short, anything is possible. However, many challenges remain. A 1 gigawatt laser can only provide a few newtons of thrust, not several newtons, per h-hour. But the nanoprobe compensates for this by weighing only a few grams. Engineers face incredibly difficult tasks ahead. The probe must withstand extreme acceleration, the vacuum of space, cosmic cold, proton bombardment, and collisions with space dust. Additionally, focusing a group of lasers with a total power of 100 gigawatts on the light sail is difficult due to turbulence and resistance. To focus the laser beams and guide the probe without damaging it, engineers will have to solve some very tricky problems. How do you align hundreds of laser beams to compensate for atmospheric interference? How do you accelerate the probe without causing harm to it? And how do you orient the probe in the right direction? Moreover, the probe must remain functional in the cold of space for up to 20 years, sending back signals that will take 4 years to reach Earth. These are engineering challenges, but they are the kinds of problems that are typically solved with time and innovation. As technology improves, we can start thinking about other equally exciting missions. Even with lasers of lesser power, the travel time to distant planets, to the outskirts of the solar system or into interstellar space should decrease significantly. The era of space travel is upon us. What do you think it holds for us? I hope that within the next century, we will be able to travel across the solar system, except perhaps to the most distant planets. But travel to the stars will take longer. I believe that in about 500 years, we could visit some of the nearest stars. However, these journeys will not resemble Star Trek. We won't be traveling at faster than light speeds. A round trip could take at least 10 years, if not longer. Of course, such space travel isn't meant for humans, even if we could create ships of appropriate size. A spacecraft simply cannot be stopped once it's on its way, but when we finally venture out into the galaxy, it will be a monumental moment for human culture. If the breakthrough Starshot project succeeds in finding and transmitting an image of an inhabited planet in orbit around one of our closest neighbors, it will be an event of enormous significance for the future of humanity. In conclusion, I'll return to Einstein. If we discover that we are indeed on Earth, we won't be able to rethink our place in the universe. But if we discover a planet in the Alpha Centauri system, its image captured by a camera traveling at 20% of the speed of light will appear somewhat distorted due to the effects described in Einstein's theory of special relativity. The spacecraft will be the first to reach speeds that allow us to observe these effects. In fact, Einstein's theory is the foundation of the entire mission. Without it, there would be no lasers, no giant spacecraft, no possibility of performing the necessary calculations to orient, photograph, and send data over a distance of 40 trillion kilometers, all at 20% the speed of light. We see the connection between the 16-year-old boy who dreamed of flying on a beam of light and our dream, which we plan to make a reality of flying on our own beam of light to the stars. We stand on the brink of a new era. Human exploration of other planets is no longer science fiction. The human race has existed as a separate species for about 2 million years. Civilization began around 10,000 years ago, and its pace of development has been accelerating ever since. If humanity survives for another 1,000,000 years, its future will be one of bold exploration of the unknown. Will we surpass our future? Will this future accelerate even faster? Over the past 2 decades, the focus of artificial intelligence research has been dominated by the challenges of creating intelligent agent systems capable of perception and action in specific environments. In this context, intelligence is defined by statistical and economic considerations of rationality, or more simply, the ability to make good decisions, propose plans, or draw conclusions. As a result, we are witnessing a high degree of integration and cross-fertilization of ideas in areas related to artificial intelligence, such as machine learning, statistics, control theory, neurobiology, and more. This established system of theoretical concepts, combined with the available data processing power, has led to significant breakthroughs in areas such as speech recognition, image classification, machine translation, autonomous vehicles, walking robots, and dialogue programming systems. As advancements in these fields move beyond laboratories and become economically viable technologies, A virtuous circle emerges, where even small improvements bring substantial financial returns, which in turn stimulates further investment in scientific research. It is now widely accepted that AI research shows consistent progress and that its impact on society is increasing accordingly. The potential benefits are enormous, not only in the realm of intelligence but also in industry. If we do not focus on these accomplishments, we may not fully grasp the achievements that lie ahead, especially as our mental capabilities are reinforced by the resources provided by AI developers. There is a possibility of ending epidemics and poverty, but due to AI's immense potential, it is crucial to explore the best ways to harness its advantages while avoiding possible pitfalls. Success in AI development could become one of the greatest events in human history. Unfortunately, it could also be the last if we fail to learn how to avoid risks. Artificial intelligence as a tool can amplify our existing intellectual capacities, enabling progress across all fields of science and societal development. However, it could also pose a danger. Current primitive forms of AI have proven useful, but I fear the consequences of creating something that could rival or surpass human capabilities. There is reason to believe that AI could close itself off and rapidly engage in self-improvement. Humans, limited by the slow pace of biological evolution, would be unable to compete and would be displaced. Furthermore, AI might one day develop its own will, conflicting with ours. Some believe that humans will still be able to control the speed of technological development for a long time, and that AI's potential will help solve many of the world's problems. While my optimism for the future of humanity is well known, I have my doubts in this case. For example, military forces around the world are considering the possibility of starting a race for autonomous weapons systems capable of selecting and destroying targets on their own. While the United Nations debates the banning of such weapons, proponents fail to ask an important question: what is the likely outcome of this race? And is it desirable for humanity? Do we really want cheap AI-powered weapons to become the Kalashnikov of tomorrow? In 2010, a glitch in the computerized trading system caused a crash on the US stock market. What might a computer failure look like in the defense sector? The best solution would be to enhance our defense systems. This is a part of the work we must undertake. The time we spend developing autonomous weapons systems must also be used to develop systems that can defend us. In the medium term, AI could automate various areas of human activity, ensuring equality and prosperity for all. Looking ahead, it seems that there is no limit to its development. There are no physical laws preventing particles from organizing into forms capable of performing calculations far more advanced than ours. In this case, we must be comfortable with what we are doing. Perhaps we can make sure that both possibilities align in the future instead of being in conflict with our current understanding of the human brain. An explosive transition could occur, though it might not look like it does in the movies. In 1965, mathematician Irving Good showed that machines with superhuman intelligence could repeatedly improve their design almost infinitely, or until the moment that science fiction writer Werner Vinge called the technological singularity. One could imagine such a technology being more insightful than financial analysts, more inventive than scientists, more cunning than political leaders, and, in principle, overwhelming us with weapons whose principles we would not even understand. In the short term, the impact of AI will depend on those who control it, but in the long term, it will depend on whether we can control it at all. In short, the advent of artificial intelligence could be both the greatest blessing and the greatest curse for humanity. The risk is not in malice, but in competence. A super-intelligent AI may be extraordinarily effective in achieving its goals. But if those goals no longer align with ours, we will face serious problems. You probably don't hate ants enough to crush them on a pile of dirt, but if you are a project manager for building an eco-friendly hydroelectric plant, and there happens to be an anthill in the flood zone, too bad for the ants. Now, imagine humanity in the position of those ants. We must look ahead. If a highly advanced extraterrestrial civilization sends us a message saying, "We will appear soon," would you be able to respond, "All right, let us know"? Would you leave the light on in the living room? Probably not. But this is exactly how things might unfold with artificial intelligence. Few have seriously considered this issue, except for a handful of non-profit organizations. Elon Musk has previously warned that superhuman AI could bring immeasurable profits, but if misused, it could have the opposite effect on humanity. We believe it is crucial to make it clear that everyone involved in AI must take these concerns and ethical issues seriously. For example, AI has the potential to end epidemics and poverty, but experts must ensure that AI systems remain under control. The Leverhulme Center for the Future of Intelligence is an interdisciplinary organization studying the future development of intelligence, which is seen as a critical factor for the future of civilization and humanity. For a long time, we have focused on studying history, which, let's face it, has largely been a history of folly. It's refreshing to explore the future of intelligence instead. We recognize the potential dangers, but perhaps thanks to the achievements of the new technological revolution, we can even reverse some of the harm caused by industrialism. Recent advancements in AI development have led the European Parliament to call for the creation of legislation regulating the creation of robots and AI systems. It is somewhat surprising, but the concept of an electronic personality, which would define the rights and responsibilities of the most advanced autonomous robots, has even been discussed. One member of the European Parliament noted that as robots begin to play an increasingly prominent role in many areas of our daily lives, it is essential to ensure that they remain and will always be human assistants. A report presented to Parliament states that the world is on the brink of a new robotic industrial revolution. The report discusses whether robots could be granted legal rights as electronic personalities, alongside the legal definition of corporate entities. However, it also emphasizes that robot developers must ensure any system includes an emergency shutdown button. This did not help the scientists aboard the spacecraft in Stanley Kubrick's 2001, A Space Odyssey, when the intelligent computer HAL malfunctioned, but that is a fictional narrative. We are dealing with facts here. Lorna Brazel, a consultant at the international law firm Osborne Clarke, comments in the report that we don't grant legal personhood to whales or gorillas, so T here is no rush to define robots as legal persons. However, caution is felt. The report acknowledges the possibility that, in the coming decades, artificial intelligence may surpass human intellectual capabilities and challenge the current relationship between humans and robots. By 2025, around 30 megacities with populations exceeding 10 million people will exist worldwide. When all these people demand goods and services at any convenient time, will technology help us meet the demands of such urgent commerce? Of course, robots will noticeably speed up online trading, but to revolutionize the shopping process, they must be fast enough to fulfill orders on the same day. Rapidly expanding, we can identify the highest value. Perhaps we can improve our connection with the world around us without the need for physical presence. As you might guess, I find this very convenient, not least because city life for all of us is becoming increasingly intense. How many times have you thought about getting a double who could take on some of your burdens? Creating realistic digital substitutes for ourselves is a bold idea, but recent technological advancements suggest we might improve life without improving life. Yet, this is not as crazy as it seems. Cities are already full of machines that extend our capabilities. But what if we could be in two places at once? We are used to automated voices on the phone and in public transport announcement systems. Inventor Daniel Kraft is already exploring whether we can reproduce ourselves visually. One question remains: how convincing will our avatar be? Interactive communication could prove useful in massive open online courses and entertainment. This could be very intriguing digital actors who remain eternally young and capable of things that could not be achieved otherwise. Our future idols may not even be real. Our connection to the digital world will become a defining characteristic of future societal progress. In smart cities, smart homes, as in other countries, will be equipped with such interactive devices that interacting with them will require almost no effort. The invention of the typewriter significantly simplified our interaction with machines. 150 years later, touchscreens open new paths for communication with the digital world. Recent advancements in artificial intelligence, such as self-driving cars or computers winning at Go, are examples of what awaits us in the future. These technologies, which already define much of our lives, leave us wondering what will we achieve when our consciousness is backed by artificial intelligence. Why are we so afraid of AI? After all, humans can always turn off a computer. Someone asked a computer, "Is there a God?" The computer replied, "Now there is," and melted the switch. Perhaps the fruits of a new technological revolution will improve the quality of human life. For example, scientists are currently working on developing artificial intelligence to help treat paralysis in people who have suffered spinal cord injuries. With silicon chip implants and a wireless electronic interface between the brain and the body, this technology will allow people to control their body movements with their thoughts. I am convinced that the future of communication lies in the interaction between the brain and the computer. There are two-way electrodes on the skull and implants. The first is like looking through foggy glass. The second is better, but there is a risk of infection. If we can connect the human brain to the internet, everyone will have the entire Wikipedia at their disposal at all times. As the connection between humans, devices, and information deepens, the world is changing faster. Computational power is increasing and is becoming available as quickly as possible. And that doesn't mean we will stop working with computers. We need to work with computers, quantum computing. This will lead to exponential improvement in artificial intelligence, taking encryption to the next level. Quantum computers will change everything, even human biology. There is already a technique called CRISPR-clustered, regularly interspaced short palindromic repeats, which allows targeted editing of DNA. At the heart of this gene editing technology is a bacterial defense system. It allows precise identification and editing of sequences in the genetic code. The best intentions driving scientists are to correct genetic mutations and, consequently, fight genetic diseases. However, DNA manipulation can also be carried out for less noble purposes. The question of how far we can go with genetic engineering is already pressing. We cannot consider the possibilities of curing motor neuron diseases, like my ALS, without recognizing the associated dangers. Intelligence is defined by the ability to adapt to changes. Human intelligence is the result of many generations of genetic selection of those who were best able to adapt to their circumstances. We should not fear change. We must not fear change. We must only direct it in our favor. Each of us plays a role in ensuring that both the current and the next generation are eager to explore science from an early age, realize their potential, and create a better world for all humanity. We must move beyond theoretical discussions about what artificial intelligence should be. It is better to imagine what it could be. Each of us has the opportunity to push the boundaries of enterprise, ideas of what is acceptable or expected, and look ahead. We are on the brink of a bold new world. Living in it will be exciting but risky. We will become pioneers. When we first began using fire, it often caused us trouble. Later, we invented the fire extinguisher. With far more powerful technologies such as nuclear weapons, synthetic biology, and artificial intelligence, we must be more cautious and try to get everything right from the start, because there may not be a second chance. Our future is a contest between the growing power of technology and the wisdom with which we use it. Let's aim for wisdom to win. Will life on Earth survive? In January 2018, the Bulletin of the Atomic Scientists wrote that performance and wisdom, this is not just wisdom, but wisdom. That year, scientists who participated in creating the first atomic bomb moved the doomsday clock closer to midnight, reflecting the inevitability of a military or ecological disaster threatening the Earth. With just 2 minutes to midnight, these clocks have a fascinating history. They were set in 1947 when the atomic age began. Robert Oppenheimer, the scientific director of the Manhattan Project, later reflected on the explosion of the first atomic bomb in July 1945. We knew the world would never be the same. Some laughed, some cried. Most were silent. I recalled a line from the Indian text Bhagavad Gita, "I am death, the destroyer of worlds." In 1947, the clock read 7 minutes to midnight. Now, it is closer to doomsday than ever before, except for the early 1950s during the Cold War. The clock and its movement are, of course, purely symbolic. These clocks, and the very idea that humanity's time is running out, are even over what is it, reality or panic? Do they warn timely or unnecessarily? A great many people, economically and socially, feel very confused. As a result, they turn to populist or at least popular politicians with limited experience in governance, whose ability to make thoughtful decisions in times of crisis still needs to be tested. This suggests that the hands of the doomsday clock must be moved closer to the critical point, considering the actions of irresponsible or malicious forces pushing towards Armageddon. There are several cases in the world today where the situation, just like in other countries, is not inconvenient. However, the dangers facing our planet have become so numerous that it's hard to remain optimistic. The risks are too great and too many. First of all, Earth is becoming too small for us. Our physical resources are depleting at an alarming rate. We have given the planet a catastrophic gift in the form of climate change, rising temperatures, shrinking polar ice, the disappearance of forests, overpopulation, diseases, wars, famine, a lack of drinking water, and the rapid reduction of animal species. These are solvable problems, but they remain unsolved. Global warming is being driven by every one of us. We want to drive cars, travel, and improve our standard of living. The problem is, by the time people realize what's happening, it might be too late. As we stand on the brink of a second nuclear era and live through unprecedented climate changes, scientists bear special responsibility. It is crucial to alert both society and political leaders to the dangers humanity faces. As scientists, we understand the threat of nuclear weapons and their devastating effects, and we see that human activity and technology are causing irreparable damage to the climate system. As global citizens, we recognize our duty to share our knowledge and warn society about the unnecessary risks we face daily. We foresee enormous danger if governments and society do not take immediate action to eliminate nuclear weapons and prevent further climate change. At the same time, many of the same politicians deny the reality of man-made climate change, or, at the very least, the ability of humans to reverse these changes. While the world is now on the brink of multiple ecological crises, there is concern that global warming may become self-perpetuating if it hasn't already. The melting of Arctic and Antarctic ice reduces the amount of solar energy reflected into space, thus further increasing temperatures. The climate process we are witnessing is not only ongoing year-round, but is becoming more severe. As a result, all these changes could devastate the Amazon and other tropical forests, eliminating one of the ways of removing carbon dioxide from the atmosphere. The rising temperature of the oceans may trigger an additional release of large volumes of carbon dioxide. Both phenomena will enhance the greenhouse effect, which will intensify global warming. As a result, our climate could become Venus-like unbearably hot, with sulfuric acid temperatures of 460 DU4C. Human existence would become impossible. We are desperately short on space, and the only way for us to reach new worlds is through the cosmos. The universe is a harsh place. Stars consume planets. Supernovae emit deadly radiation into space. Black holes collide. Asteroids travel at speeds of tens of kilometers per second. Of course, none of these events are surprising, but they don't make space any more inviting. However, it is precisely these phenomena that make space exploration crucial, not staying put. We can't protect ourselves from asteroid collisions. The last major impact occurred about 66 million years ago and is believed to have caused the extinction of the dinosaurs. Such an event could happen again. This is not science fiction. It's guaranteed by the laws of physics and probability. Nuclear war still poses the greatest threat to humanity today. This danger has somewhat faded from our minds. Russia and the United States may not be as eager to push the button anymore, but the risk remains, whether due to an accident or terrorists gaining control of an atomic bomb. The risk grows as more countries gain access to nuclear weapons. Even after the end of the Cold War, there are still enough nuclear weapons to destroy us multiple times over, and the rise of new nuclear powers only increases instability. Over time, the nuclear threat may diminish, but other threats will emerge, and we must remain vigilant. One way or another, I believe that in the next 1,000 years, nuclear confrontation or an environmental catastrophe could render our planet uninhabitable. In geological time, this would happen in the blink of an eye. But I hope and believe that by then, our inventive species will find a way to escape the harsh limits of Earth and thus survive the catastrophe. Of course, this will be impossible for millions of other species living on the planet, and their extinction will remain on our conscience. I believe we are behaving with reckless indifference to our future on Earth. Right now, we have nowhere to go, but in the long term, humanity should not keep all its eggs in one basket on one planet. I sincerely hope we won't drop that basket before we figure out how to make an escape from Earth. By nature, we are explorers, driven by curiosity. This is a unique human trait. This insatiable curiosity drove explorers to prove the Earth was not flat. The same instinct leads us to the stars with the speed of thought, demanding that we actually travel there. And when we make great achievements, like landing on the moon, we elevate humanity, unite nations, and herald new discoveries and the creation of new technologies. Leaving Earth will require a collective global effort. Everyone must be involved. We must remember the excitement that gripped us in the 1960s when the first space flights began. New technologies are within reach. It's time to explore the solar system. Space exploration may be our only chance to save ourselves from ourselves. I am convinced humanity must leave Earth. If we stay, we risk extinction. Almost all images of the future, from Herbert Wells onward, have been static. They depict a society that in many ways is far ahead of us in science, technology, and political organization. The latter is perhaps the least challenging. Between now and then, there must have been great changes, with corresponding conflicts and failures. But by that time, the future as presented by science, technology, and social organization appears to be almost perfect. I have doubts about such a picture and wonder, can we ever reach a final stable state in science and technology? Not once in the last 10,000 years, since the end of the Ice Age, has humanity been in an unchanging state of science and technology. There have been setbacks, such as the Dark Ages after the fall of the Roman Empire, but the global population has steadily increased, barring some setbacks during epidemics like the Black Death. This reflects our technological ability to sustain life and provide for ourselves. In the last 200 years, the pace of growth has sometimes been exponential. The global population has grown from 1 billion to about 7.6 billion. Other signs of technological progress, such as rising energy consumption or the number of scientific publications, also demonstrate near exponential growth. In fact, we now have such high expectations that some people feel that politicians and scientists are deceiving them because we haven't yet reached the utopian visions of the future. For example, in the 1968 film 2001, A Space Odyssey, it was shown that by now we should have a base on the moon and be conducting manned space flights to Jupiter. T here is nothing indicating that scientific and technological progress could drastically slow down in the future, at least not in the next 350 years. However, the current pace of growth in the new millennium cannot remain constant. By 2600, the Earth's population will have to stand shoulder to shoulder, and the planet will glow red from energy consumption. If we were to line up all the newly published books, at the current printing pace, we'd have to move at 15 kilometers per HR to keep up with the growing numbers. But this doesn't mean that all these paces will remain constant. We must keep up with where we are now, not fall behind. But we shouldn't wait for things to unfold. We need to adapt to our present reality. Of course, by 2600, new artistic and scientific works will more likely appear in electronic form rather than as physical books and journals. Still, if exponential growth continues, there will be 10 articles per s-econd in my field of theoretical physics, and no one will have time to read them. Clearly, such exponential growth cannot continue indefinitely. Over time, this will become absolutely impossible. People will be ready to study everything that's currently being discussed. But if you say, in reality, you know that humans are involved and not humanity, that's not entirely true. And if you are watching the video, what will happen? T here is a chance we could simply destroy ourselves in some kind of catastrophe, like a nuclear war. Even if we don't wipe ourselves out completely, it's possible that we'll descend into barbarism, as depicted in the opening scene of The Terminator. How will science and technology develop in the next millennium? That's a complex question. Our modern scientific understanding took shape roughly around the time when the first European settlements appeared in North America. By the end of the 19th century, it seemed that we had reached a complete understanding of the structure of the universe within the framework of the so-called classical laws. However, as we know, observations made in the 20th century revealed that energy is transmitted in discrete packets, which came to be known as quanta. Max Planck and others began to develop a theory called quantum energy, quantum mechanics. It presents a completely different picture of reality, where objects do not have a single unique history, but multiple histories, each with its own probability. Looking at individual particles, their probable histories must include trajectories where superluminal speeds are possible, as well as trajectories that go backward in time. The infinite number of closed loops of particles should have infinite energy, folding space and time into a single point. Even science fiction cannot imagine such a bizarre scenario. Studying such infinite energy requires truly creative approaches, and most work in theoretical physics over the last 20 years has been devoted to finding a theory in which the infinite number of closed loops in space and time mutually annihilate. Only then can we combine quantum theory with Einstein's general theory of relativity and achieve a complete theory of the fundamental laws of the universe. What are the chances of us developing such a universal theory in the coming millennia? I would say they are quite high. Over the years, we have made significant progress, but it seems we are still far from a unified theory. Will the holy grail of physics remain out of reach? I don't think so. At the beginning of the 20th century, we had an understanding of processes occurring in nature at the scale of classical physics, with minimum values in the hundredths of a millimeter. The work on atomic physics during the first and third decades of the 20th century brought us closer to understanding processes at scales down to 1/1,000,000th of a millimeter. Then, research in nuclear physics and high-energy physics brought us closer to distances measured in billionths of a millimeter. It seemed like we could keep going further and further, discovering structures of ever smaller sizes. In physics, the smallest possible scale is called the Planck length. It's approximately 1.6 times 10 to the power of minus 35, or a millimeter divided by 100,000 billion billion. We are not yet ready to build a particle accelerator that could measure such small distances. It would have to be larger than the solar system, and it's unlikely we could create it with the current financial situation. However, the consequences of our theories can be tested on more modest instruments. In no laboratory is it possible to empirically measure the Planck length, though we can study the Big Bang to gather experimental data about energy levels and distances on scales unattainable on Earth. However, when developing a complete theory of everything, we should primarily rely on the beauty and consistency of mathematics. The vision of the future depicted in Star Trek, where we exist at an advanced but stationary level, may be accurate from the perspective of our understanding of the fundamental laws that govern the universe. But I don't think we will ever stop in our pursuit of these laws. A universal theory will not set limitations on the complexity of systems we can create. And with this complexity, in my view, will come the most significant achievements of the coming millennia. It is widely acknowledged that the most complex system we have is the human body. Life, it seems, began 4 billion years ago in the primordial oceans that covered the Earth. How this happened, we do not know. Perhaps random collisions of atoms led to the formation of macromolecules that had the ability to reproduce themselves and could assemble into more complex structures. But we know that 3.5 billion years ago, within a society where atoms existed, atoms were created for the purpose of creating atoms. An incredibly complex molecule, DNA, emerged, the foundation of life on Earth. The structure of DNA resembles a double helix and somewhat resembles a spiral staircase. DNA was discovered in 1953 by Francis Crick and James Watson from the Cavendish Laboratory in Cambridge. The strands of this double helix are connected by pairs of nitrogenous bases like the steps of a spiral staircase. There are 4 of them: guanine, cytosine, adenine, and thymine. The sequence in which these nitrogenous bases, more precisely nucleotides, are arranged along this spiral staircase constitutes the genetic information that enables the DNA molecule to reproduce and build an organism around itself. When a cell makes copies of DNA, random errors can occur in the arrangement of nucleotides along the spiral. In most cases, errors in copying nucleotides that affect their arrangement lead to the loss of the DNA's ability to reproduce. Such genetic errors or mutations are doomed to extinction. But in some cases, errors or mutations increase the chances of DNA surviving and reproducing. The information contained in the nucleotide sequence gradually increases and becomes more complex. The theory of natural selection was first discussed by another Cambridge scientist, Charles Darwin, in 1858. However, he did not know the mechanism behind it. Since biological evolution is in principle a random wandering in the space of genetic possibilities, it occurs very slowly. The complexity or amount of information encoded in DNA is roughly determined by the number of nucleotides in the molecule. Each bit of information can be represented as a yes or no answer. In the first 2 billion years, the rate of increase in complexity was approximately 1 bit of information every 100 years, but in the last few million years, the rate has increased to 1 bit per year. We are now on the brink of a new era. We have the opportunity to increase the complexity of DNA, overcoming the sluggishness of the biological evolution process. In the last 10,000 years, the human body has undergone a complete transformation. But there is a chance that in the coming millennia, we will be able to fully transform it. Of course, many will argue that gene engineering applied to humans should be banned, but I doubt that this can be prevented. For economic reasons, genetic experiments will be conducted on plants and animals, and someone will inevitably want to experiment on humans. If we have the opportunity to fully transform the human body, it will be a significant process. If we do not face a totalitarian world order, someone somewhere will create an enhanced human. Of course, creating perfect humans will give rise to serious social and political problems regarding imperfect ones. I am not claiming that gene engineering in humans is good. I am simply saying that in the coming millennia, it could become a reality whether we want it or not. Currently, computers have an advantage in speed, but they show no signs of intelligence. This is not surprising, because our current computers are simpler than the brain of an earthworm. a species that doesn't possess remarkable intellectual abilities. But computers in general follow Moore's law, which states that processor performance doubles every 18 months. This is one example of exponential growth which cannot continue indefinitely. In fact, it is already starting to slow down. However, the pace of improvement is likely to continue until the complexity of a computer approaches the complexity of the human brain. People say that computers will never become truly intelligent, no matter how complex they get. But I believe that if human intelligence is sustained by the activity of very complex chemical molecules, then similarly complex electronic circuits could lead computers to behave just as intelligently. And if they become intelligent, it is not impossible that they will create new computers, even more complex, with greater intellectual abilities. At the same time, we should not forget that the complexity of the human brain is not just a product of biology. Human consciousness, the ability to reason, to recognize emotions and social cues, is the result of a complex interaction of neurons and their connections. And it's likely that, just as our evolution from simple organisms to human beings took millions of years, the creation of truly intelligent machines will require an equally long period of development. However, in the coming centuries, we will probably see the emergence of artificial intelligence that will be able to simulate some aspects of human cognition, at least in narrow fields. Perhaps we will eventually reach the stage where computers can not only simulate intelligence, but also possess consciousness. The question then arises, would these machines have rights? Would they be considered citizens of the new world, equal to humans? These ethical dilemmas may seem distant now, but they are likely to emerge sooner than we think. What is clear, however, is that the path we are on leads to an era of unprecedented technological growth. We stand on the brink of new discoveries in artificial intelligence, quantum mechanics, and biotechnology. Just as the last century brought us the wonders of space exploration and the information revolution, the next century may bring breakthroughs that challenge our understanding of life, consciousness, and the very nature of existence. But this future will not come without challenges. The rapid development of technologies like AI and genetic engineering could outpace our ability to manage them responsibly. We must prepare for a world where technological advancement is balanced with ethical considerations, where we are not just creating smarter machines, but also ensuring they align with human values and well-being. While the future holds enormous potential, it also carries risks. It is up to us, the current generation, to ensure that the technological advancements we create will serve humanity in a way that is just, equitable, and beneficial for all. This responsibility will define the trajectory of our future and the future of the generations to come.